Three, two, one, let's go. Alright, so, what's the plot for today? Today we are going to attack variable coefficient differential equations, and we're pulling out the big guns to solve them. Alright, so, let's remind ourselves of the setup. Every second order linear homogeneous differential equation looks like this. And every differential equation solution looks like this, where y1 and y2 solve the differential equation, meaning that if I plug y sub 1 into this dE right here, I will indeed get 0. And they are a fundamental set of solutions, meaning that y1 and y2 are linearly independent. So scaling and adding them together creates a new function. Scaling and adding them together is not trivial. It actually produces something new. All right. Now, as we've been saying for the past couple of weeks here, even the most reasonable second-order linear homogeneous dE, the solutions can be very challenging. So the classic example is the Airy equation, this one right here, y double prime minus xy equals 0. The solutions to this cannot be expressed using our familiar functions. So usually you refer to such functions as special functions, or also sometimes called transcendental functions, and basically saying that, well, they can't be represented in closed form using the algebraic functions, which are the polynomials, exponentials, logarithms, trigonometrics, and so on and so forth. Okay, so that means, well, what do? Right? So these functions, the solutions to D, these have been studied to death. The Airy functions have a very rich history. To go to the Wikipedia article or, anything else. Any book about special functions, as I mentioned, will go into the Airy equations, the Airy functions, and similar things. So our goal for today is to kind of go, all right, well, how do we get a handle for these things? How do we understand such differential equation? How do we understand such solutions? Okay. So one method of attack is to go back to Calc 2 and remember your favorite part of Calc 2. Sequences and series. Okay, so the next couple of slides here are just going to be kind of a quick crash course of some of the stuff we talked about in Calc 2. But it's worth noting, I just want to hammer home some of the finer points about this topic, because we're going to use this stuff to solve DE, so we really, we want to just, let's get ourselves all on the same page and up to speed. Okay, so by a sequence, I mean an enumerated list of numbers. It turns out that a sequence doesn't necessarily need to be a list of numbers. It can be a list of anything, but for our purposes, it will just be a list of numbers. And formally, what that means is that it's just the function. It's a function that you give it positive integers, and it spits out stuff, right? It enumerates it for you. It gives you a first, it gives you a second, it gives you a third, it gives you a fourth, so on and so forth. Okay. Now, we will denote sequences, so the notation that I like using is this one right here, right, indicating that n starts at 1, goes off to infinity, and x sub n is, the output for the positive integers n. So we're worth noting that there's a lot of other notation that a lot of people use for this stuff. This is the one that I like. Some people hate this notation, some people love it. I like it. I think it clearly communicates what's going on, but whatever. Don't need to get into too many things there. But the thing that we care about sequence is because it is a function, that means we can take its limit. Specifically, the limit of the sequence is the limit of the function. And we write it using the usual notation. And it's worth noting that this is, of course, a limit going off to infinity. So it is a special case, but it is there nonetheless. Okay. So for some quick examples, just to jog our memory, the limit as n goes to infinity of 1 over n is equal to 0. And something like the limit as n goes to infinity of I to the n. Ooh, there's a fun one. What would that do? Well, think about the powers of I. I to the 1 is I squared is negative 1. I cubed then would be negative I, and then I to the 4th would be 1. I to the 5th would be I, because it's I times I to the 4th, and so on and so forth. So the powers of I actually cycle between 1, I, minus 1, minus I, and since they cycle and never settle down, they don't approach something, they don't get close and stay close to something as n gets arbitrarily large. Since they cycle, this limit does not exist. Okay. Now, we're not going to get so sweaty about the nitty-gritties and the details of sequences here, because these are really just the tool for the star of today, which is the series. So, if you give me a sequence, I can form its series, which is the limit of the sequence of partial sums. So, I take a sequence, I create a new one by adding up the terms and stopping at a given point. So the first term is just x1, the second term would be x1 plus x2, the third term would be x1 plus x2 plus x3, and so on. So the series then is the limit of this sequence, and the limit is written in two different shorthands. So one is to, hey, you're taking the limit, so just put the infinity sign up there. The other way to write it, and the way that it was traditionally written for a very long time, was to do, x1 plus x2 plus x3 plus, yada, yada, yada. So that's two ways that we're going to denote series. We'll jump back and forth between the two. I am very partial to the sigma notation. I know a lot of people hate sigma notation and hate dealing with it and would rather write it out like this. But I'm hopefully going to convince you that while this is nice and intuitive, it sometimes leads you down the wrong path. But keep in mind, though, these are just shorthands, right? These don't represent. Right, and one of the reasons I hate this is that this is not a summation. It looks like it's a summation, but it's not. Remember, it is shorthand for a limit. So we need to keep that in mind whenever you deal with this, and we're gonna talk about that, let me tell you. Alright. Okay. Now, like I just said, need to be careful. Since it is a limit, we need to be careful about its manipulation. So we're going to have to play around with these things because we want to use them to solve series. We want to use series to solve differential equations. That's what I meant to say. But it's a limit, so limits are very nice and they're very intuitive, but they are a little testy, right? They're a little sensitive. If you don't treat them right, they're gonna get revenge on you, as I'm sure you've experienced with some fun limits. Okay, so let's talk about things that we're actually allowed to do with series, specifically things we will be doing to solve DEs. So the first thing to note, and this is a very powerful tool, and that is this idea of re-indexing a series. Right, so when we talked about sequences, we're like, okay, you start at 1. There's nothing stopping us from starting wherever we want. We usually start at 1 because, you're like, oh, the first thing, and then the second thing, and then the third thing. So that's, naturally how we do. If you're a filthy computer person, maybe you like counting at 0. So sometimes we'll start at 0. Other times we may start somewhere else. And it's worth noting that it really doesn't matter. We could start it at negative 4 billion if we wanted to. We don't need to squabble over it. But it is worth noting that when we do re-index the change to the starting point, we need to change the indexing accordingly, right? So this summation right here, right, n is equal to 1. That means on the left side here, I've got x1 plus x2 plus x3, and I have got the limit of that sequence of partial sums. Here, if I start at 0, well, the index needs to respect that, right? And a way I like to think of it is, well, I'm taking 1 here, and I'm stealing it away. So since I am taking 1 away, it needs to go somewhere. So, plus 1, right? 2, right? I need to lose something, right? I need to, if I want to go from, I'm saying it wrong. If I want to go from 1 to 2, well, I need to add something. I need to add down here, which means I need to steal that 1 from somewhere, so I stole it from the indexing, right? So that's one way of thinking of it, right? If I need to go from 1 to 0, that 1 needs to go somewhere. If I need to go from 1 to 2, well, that 1 that I need to add needs to come from somewhere. Another quick check for it is, well, just plug in, right? Plug in n equals 1, plug in n equals 0, plug in n equals 2. All of them give you a starting index of x sub 1, so it's all legit. Okay. So reindexing is a technique. It shows up. It's useful, and we're going to use it. And it's one that I really want to stress is incredibly powerful. I actually, in my own research, had to reindex a series to make it do what I wanted it to do. And I remember my advisor. Uh, I love my advisor, but what made my advisor great was that it was impossible to please him in a way. Like, very rarely did you get a good job out of him. You always got a, yeah, okay, you did it, that's all right. I remember I was still one of my graduate classes I was taking. I did a really good job on one of the homeworks, so the professor wrote truly excellent work on the top. And when I showed it to my advisor, and he scoffed and said, "Never expect me to say anything like that to you." Anyway, but so for that problem I was working on when because he had worked it out and I was explaining how I thought of it, and I hit the point where he's like, "Okay, now here's that crappy part with the series," and I paused. I was like, "No, you just reindex it. What are you talking about?" And his eyes lit up, and he was like, "Oh, you're right." Yeah, yeah. I cherished that moment because I think like within a couple minutes later, he was yelling at me about how dumb I was. So, oh, anyway, so something else you're allowed to do about series. By the way, I love series. While we're here, this is my favorite mathematical object. I love playing around with these things. They're very fun. Something else we're allowed to do is peel off some terms from the beginning, right? So, the series starting from 1 going to infinity. Well, I can peel off the first term, and then what's left over is still going to be the limit, right? But, you just took a term off. So the way I like to think of this is like, well, we've got the whole beach right here, and I went to the beach, and I took like a handful of sand. The whole beach is still there, but it's missing the handful of sand. And then I go back and I took another handful of sand. Right, the whole beach is still there, but now I've got 2 handfuls of sand with me. So on and so forth. So we can peel off any number of finite terms off the beginning. So these 2 maneuvers, reindexing and peeling off, I don't know of a better name for this other than peeling off. For our international friends, I hope that translates well. But anyway, so the other things we could do algebraically of series is scale them. So if you scale a series, it's the same thing as scaling the individual terms. So another way of writing that is, well, if I scale that summation, I can scale individually. And that's not too surprising. The limit, if you scale a limit, it's the limit of the scaled function, so that works out pretty great. Same thing with addition. If I add 2 series together, it's the same thing as adding them up term by term. So this move right here is allowed. If I have a series plus a series, I can group them the way you want. And that also shouldn't be surprising because the sum of a limit is the limit of the sums. And there we go. Now, it's worth stressing that these 4 techniques I just showed you, reindexing, peeling off terms, scaling, and adding series, these are pretty much it when it comes to the manipulations you can do to a series. It gets very dangerous when you start trying to do other things. And if you're like wary about series, and we hit this part of the course, and you're like, "Oh God, I hated series. It was the worst part of Calc 2." I want to stress to you, there's a very good reason, and it's the series right here. Series really were not very well understood for a very long time. It really wasn't until the 1800s where people really, really got a hold of how series are supposed to behave. And the offender, the one that really indicates why people had such a hard time with series, is Grandi's series right here. The summation from n equals 0 to infinity of -1 to the n. So if we write out the partial sums, right, what is this going to look like? Well, it's 1, then -1, then +1, then -1, +1, -1, so on and so forth. Okay. So we just discussed ways of algebraically manipulating series. If you try to start manipulating this thing, you're going to start getting all sorts of bizarre stuff. Okay. So Grandi's series was a very contentious topic. for a variety of reasons. So the first thing most people do when they see this, they look at it and they go, "Oh, okay, this should equal 0." Right. So, right, if I slap parentheses naturally where you would want to put them, oh, hey, the ones and the minus ones cancel out. There's infinitely many of those pairs. They all cancel out, so the series equals 0. But, right, it's, hey, straightforward, seems legit. Okay. Until you realize that your little trick there, well, if you just shifted the parentheses over, well, that would tell you the series is equal to 1, and we definitely know 0 and 1 are different. So we immediately see that parentheses can't just be placed wherever we want with a series. And that should be surprising, because if I added up a finite number of numbers, I can put parentheses wherever the hell I want. It doesn't matter. Summation is addition. So, summation is addition. Addition is associative. That's the thing I wanted to say. Jeez. Ugh. I need more caffeine, man. I don't know what's going on here right now. But anyway, so addition is associative, so it doesn't matter we put parentheses. Here, though, we see it falling apart. And again, the reason this is falling apart, and the thing that took forever for mathematicians to really finally agree on and get a grip on, this thing on the right is a limit. There's no actual algebraic stuff going on here. This is a limit. It's not an algebraic expression. And it took a long time for that to really take hold. So last time we introduced our new good friend Augustin Cauchy, and he was really the first one who looked at this thing and said, "You know what? You know what this is?" He looked at this and he said, "This is bullshit. That's what this is." And everyone stood up and clapped. That student's name was Albert Einstein. And yeah. Cauchy, he's one of... so the Eiffel Tower has a list of 72 names on it. Cauchy's one of the names, by the way. But anyway, okay, so Grandi's series here reveals to us that, the things like this kind of parentheses plainness, we can't do that for a series. That you can't make sense of that. And it gets even sillier, because I could take these terms and rearrange them. So, for example, instead of doing 1 minus 1 plus 1 minus 1 plus 1 minus 1, how about we do 2 pluses? So a plus, then a plus, and a minus. Right? I have infinitely many plus ones, and I have infinitely many minus ones. So let me just, I'll put 2 pluses and then a minus. 2 pluses and a minus. Now, what happens here if you slap some parentheses on it? Well, hey, the 1 and the minus 1 knock each other out, but then I've got these lonely ones that creep in. So, Grandi's series then, not only could it equal 0, not only could it equal 1, but now I can make it as big as I could ever want it. And in fact, you can do these sorts of manipulations to make it equal whatever integer you want it to equal. So, what's the answer then for Grandi's series? Well, I kind of already let it slip. The partial sums. If you look at the partial sums, if you stop at an odd spot, so if you stop at the first spot, you get 1. If we stop at the third spot, we'll get 1. If you stop at the fifth spot, you'll get 1. Now, if you stop at an even spot, so if you stop at the second one, you'll get 0. If you stop at the fourth spot, you'll get 0. If you stop at the sixth spot, you'll get 0. The partial sums alternate, so the limit doesn't exist. Right, and this, like I said, this really didn't become the accepted answer until the 1800s, when people finally kind of went, okay, well, when we talk about a series, this is exactly what we mean. We'll talk in a little bit. Another value, another popular value for what Grandi's series should equal is 1/2, and we'll talk about that in a little bit. You may have seen an internet video with a bunch of dumb guys from the University of Nottingham talking about things. They like numbers, but they don't know how they work, so it's great. Alright, so speaking of classic examples of series, let's get another one. It's going to tie into everything here. The summation of 1 over powers of 2. So 1/2 plus a fourth plus so on and so forth. So it turns out that, not too tricky, you can actually show this equals 1 minus 1 over 2 to the n. It's not too hard to convince yourself this is true if you just kind of think about it. If you start at 1/2, right, that's half of 1, so 1 minus a half, so that works. If you take a half and add a fourth to it, and we think about that in terms of 1, well, we've got 3/4. So we've got what's left over, right? We took a fourth away from 1. And that goes on. Another way of deriving it, multiply both sides by 2 to the n, and you can kind of see why it ends up working out the way it does. But anyway, because of this, the limit of that goes to 1. And this specifically is an example of a geometric series, and that trick I just described of multiply by 2 to the n and manipulate it, that in general works for any summation of x to the n, like this. So here we go. If you do n equals 0 to the infinity, x to the n, this will always equal 1 over 1 minus x, as long as x is strictly between -1 and 1. And the reasoning for that is because if you look at this right here, you will end up dealing with a 1 over x to the n term, and that will only go to 0 if if x is less than 1. So yeah, you need to be careful there. Now, like I was just mentioning, Grandi series, a value that some people say it should have is 1/2 because, hey, plug in -1 into this equation. Oh, well, you'd get 1/2 here. But, like I just said, that formula is going to use a limit at some point, and that limit will only work if x isn't equal to -1. But that didn't stop Euler. Like I've mentioned before with Euler, as great and as smart as Euler was, there were a lot of things where he just did whatever the hell he wanted. He didn't care. So another proposed value for Grandi series is 1/2, and there's actually a way to make that work with something called Cesare summability, but that's going off the deep end. All right, let's wrap all this around. I had my fun here. I've been rambling about series for like 15 minutes, so let's get to it. I totally forgot about. I got one more spicy meme for you here. My other favorite thing in math. This argument doesn't really happen too much more on the internet. I don't think. Everybody's too busy arguing about whether or not division is associative, and that's really annoying. Like, you ever see that, like, I got 2 divided by 4 times some stuff in a parentheses, and it's like, what's the answer supposed to be? And it's like, that doesn't mean anything. But this one, on the other hand, this one, I'm going to convince you. Point I'm repeating and 1 are the same number. Deal with it, and here's why. All right. So the reason these are the same. Well, what would point I'm repeating really mean? Well, first off, point I'm repeating, that means 0.0, 0.9, and 9 going on forever. That means a limit is happening, right? And specifically, right, a 9 in the 10th place, a 9 in the 100th place, a 9 in the 1000th place, so on and so forth. Hey, we have a series, which, by the way, I'm allowed to factor a term out of. And, oh, hey, look, what do I have there? I got a nice geometric series. Specifically, I got this one, and hey, that's less than 1. Pop it into the formula, and oh, would you look at that? You get 10/9. 9/10 times 10/9, boom, it's 1. There you go. Point I'm repeating is 1. I feel like people don't really argue about this one anymore, but anyway. Okay. I forgot I had that slide here. I wanted to do a little. Well, listen here, man. Listen here, you Butler stands. I'm the dankest meme lord in the math department, so. Alright, anyway. Okay, so let's actually get into it. How are we going to use all this fun stuff here to solve differential equations? So, that geometric series we just saw is actually a special case of something called a power series. So a power series is basically a infinitely long polynomial. Right, but we need to be very careful about what we mean there. So remember, the way a polynomial normally works is you've got coefficients, you feed me x gets powered and then scaled and added up. So a power series is that idea, but then we go one step further and take a limit. So you give me an x, I compute the series, and that's it. Okay. So, like we just saw, this power series is actually equal to this function, but as we stressed, the power series is only defined on the interval -1 to 1. It equals this function, but note, this function's domain goes beyond that. So that shouldn't be too surprising, because we've already encountered this in differential equations, where we'll have things that are going to work as a solution to the DE, but the domain for the DE is not the same as the domain as the function. And in general, power series are defined on intervals. So if you remember from Calc 2, we talked about radius of convergence and all that other fun stuff. We're not going to get too heavily into that, but I will point out, again, the spots where domain becomes a thing we got to think about. But for the most part, we can kind of circumvent that. But, alright, so that gives us a nice little example of power series, right? So note, right, probably the easiest one where all of the coefficients are just 1. Make life as easy as possible. Alright, and like I said, something that we've already experienced in C and DiffyQ is something having a domain that's different than the domain of what it's technically equal to. Alright, so how are we going to use these to solve differential equations? Well, I need to be able to take derivatives, and power series can be derived. So if I have a power series, its derivatives are what you think they should be. Right? It's a polynomial, infinitely long. So when you take its derivatives, they should do what you think they should do. Right? Power rule applies, constant terms get killed, and yeah, that's literally how it works. So here is the nice compact way of writing it. And here is if you want to write it in the other notation. Right, this notation I feel like communicates it a little bit more cleanly and why that works, but yeah. And this goes so on and so forth. That's kind of nice. So you can take as many derivatives as you want. We're not going to exceed 2 derivatives, but it's possible to go beyond that. In fact, you can take infinitely many derivatives. And something that I then want to note is that if we were to plug in 0, f of 0 has to be the constant term of the power series. F prime of 0 would also be the constant term, which is f of 1. F double prime of 0 is the constant term, which in this case is 2c2. And hopefully this formula is somewhere in your mind. The nth derivative of a power series evaluated at 0 is always equal to n factorial times the coefficient. Yeah. Nice. All right. So now that we got that, let's attack differential equations. So we're going to use them to solve DEs. So let's start off with a DE we already know the answer to. Let's see how all this stuff kind of works and comes together. Okay. All right, so y prime equals y. We know how to solve this one. But let's solve it using power series. So let's let y equal a power series. I'll take its derivative, as we just discussed. It's just take the derivative of this thing. X is the variable. Everything else is right constant going along for the ride. You take derivative of x to a power. Power goes to the front. You take 1 away. Here we go. Now, these two things are equal to each other. Here. So what do we do then? Okay. So the secret sauce to this method is to remember something about polynomials. Right, as we talked about, two polynomials are equal precisely when their coefficients are equal. Well, we could use that in this case, but it might be a little messy, so let's not do that. Instead, let's do this. A polynomial is equal to 0 when its coefficients are all equal to 0. So let's get it all on one side of the equation. Okay. So specifically, a power series, like polynomials, could only equal 0 if all the coefficients are 0. Okay. So let's set it equal to 0, and bleh, we get all of this. So I'll unpack everything here. But something I want to note, I'm calling these cute moves with quotes around it. Because, I'm writing everything out here in sigma notation. You can write it using the other notation where you actually write out the sums, and you'll get the same thing you get here. Some people like that a lot better. Specifically, Professor Andriotti likes that better. Spring 2020, this past spring. I was trying to think, when was that? I was like, oh yeah, that was like in February. Anyway, we were talking about this, and we were talking about sigma notation, we were talking about derivatives like this, and he was, so I was talking about, like, oh, you take the derivatives, you do the reindexing and all that stuff, and he was like, yeah, the cute moves, you can do those, I thought it was funny he called them cute moves. They are cute, they're really nice, I like these moves, but anyway, so, we've got the power series here and the power series there, so I subtracted it over. Now, I want to turn it into one power series, because, right, I want it to equal 0, so I can get all the coefficients to equal 0. Now, since I'll subtract this over here, now I want to combine them together, but there's a couple of obstacles into combining them. So the first thing is that, well, they start at different locations. So there are a couple of ways of circumventing that. One way is to reindex, and another way is to peel the term off. Now, in this case, reindexing them gets us starting at the same spot. Now, the next thing we want to look at is, all right, well, is it a x to the n, right? So when we add the two series together, will it pull apart nicely? So in this case, a simple reindex, right? So note here, I want to go from n equals 1 to n equals 0. So that means the 1 needs to go somewhere, so the n's will become n plus 1s. And then now when I combine these, well, they combine together really well. All right, so subtract this over. I have a 0 now. On the left-hand side, I have a power series equal to 0. The only way that's true is if that equation right there holds for all n. Okay, nice. Okay, so now we've got that. So what do we do? But what do we do now? Well, now that we've got this, I claim we've solved it. All right, and you might be looking at this going like, what's going on, man? What is this? Come on, dude. What are you doing to me? Well, what I'm doing to you is giving you the goods, because that equaling 0, we can solve for c sub n plus 1, and this now gives us a recurrence relation. Specifically, now I get a formula telling me how to get any term out of the coefficients for the power series based on the previous ones. So I can now start spitting out some information. I can start spitting clean facts at you. Specifically, c sub 1, so if I plug in n equals 1, 0 into this equation, has to be equal to c0. C sub 2, plug 1 into this equation, has to be c1 over 2. Well, I know what c1 is. It's c2, so I get that. C3, plug 2 into the equation. I know it's C2 over 3. Well, I know what C2 is from the previous step. It's C0 over 2, so I get C0 over 3 times 2, and keep going. Hey, boom. C sub n is C0 divided by n factorial. There we go. Nice. So this recurrence relation gave me a way to explicitly compute what the coefficients need to be. And note that all of the coefficients only depend on one unknown parameter. I have a first-order differential equation. Its solution should be a one-parameter family of solutions. I now have one parameter. So if I go to my power series, all of the c sub n's are c naught over n factorial. I can pull out scalars out of the series, and hey, I've now got a one-parameter family of solutions to my DE. Beautiful. Cool. And now I can go even further. If I wanted to solve an IVP, I know what C naught is in terms of the derivative of y. So if I had the IVP y prime equals y of 0 is 2, C sub 0 is y is 0. So that's just the 2. Boom. Done. Boom, 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 boom. Nailed it. Right. Freaking checkmate Diffie Q. Nailed it. All right, cool. So, hey, there you go. That's how you use power series to solve a differential equation. And of course, it's worth noting, hopefully this one is burned in your brain, and I've already talked about it in this class. E to the x is equal to the summation of x to the n over n factorial. It's probably the most famous series of all time. And as I've stressed, it's probably, this right here is probably the single most important equation in mathematics. There's a lot of things that have a claim for that, but this right here is the power of this, not just in mathematics, but how it pertains to all fields of sciences. It's like, exponential growth, of course, is something that's makes an appearance everywhere, and having it connected to series like this, it's very powerful, very important. So yeah, good stuff. All right, but this is these are baby weights. Let's lift the big plates. So here we go. The Airy equation. We're finally going to take this one down. We're finally going to get some answers. What are the solutions to I double prime minus x times y equals 0? What do these look like? Okay. All right, now going into this one's going to have a lot more moving parts than the one we just saw. Right, so the one we saw had a reindexing. This one's also going to have reindexing, but it's also going to have all those other tricks we were talking about, like peeling off terms, grouping things together, right, using the additions and the factoring out tricks accordingly. So this one is this one's going to test our might. So let's go. All right. So y is going to be a power series, right? So set y equal to a power series. So c naught plus c1 x plus c2 x squared plus yada yada yada. Compute its first derivative, compute its second derivative. Now we're going to plug that in and deal with it. Okay, so get ready. There's the avalanche of stuff. All right, it's a lot to unpack here, so let's talk about it. Okay, so the area equation, y double prime minus x times y equals 0. All right, well, y is our power series, c sub n x to the n going from 0 to infinity. Its second derivative, computed like that, gives me this here. Now, the first thing I do, it's worth noting that all of the moves that I'm about to make here, you can do them in different orders, but the order that I'm doing here is probably the cleanest way of doing it. Right, like I'm going to distribute the x at my next step here. You could have done the re-indexing first if you felt like it, if you want to move, left to right. Really doesn't matter how you attack it, but there are some things that you do need to generally keep in mind. So the first thing we want to do, so here we have an x to the n minus 2 and an x to the n plus 1. Well, right, we want to group it together and get, rewrite it as one power series. So we're going to want to get an x to the n term in both of the series symbols. So let's reindex this to be x to the n and reindex this one to be x to the n. So note, two different types of reindexings are going on. I need to go from 2 to 0. So the 2 needs to be added to the terms. So n gets replaced with n plus 2. And I need to get rid of this 1. So the 1 needs to go here, meaning I got to take 1 away from the n's. Okay, so we have the x to the n, so they're going to match, so we'll be able to factor that nicely. Next thing we see, well, we don't start at the same spot. Here we start at 1, here we start at 0. Okay, so I need to peel a term off of this one, right? And again, that is a legal series maneuver. And now we have the common x to the n, the common x to the n, the same starting point, the same starting point. So we can combine this into one series like that. All right, and now we have our power series where for the x terms, x squared, x cubed, the coefficients are following a very nice, clear pattern. But the first term is just doing whatever the hell it wants. And that's kind of an unfortunate thing that does happen with power series solutions. Sometimes you'll get a couple of terms in the beginning that just, they're doing whatever they want. They don't care what you're doing. They're just going to hang out by themselves and be like, I'm doing my thing. You guys get your recurrence relation. We're just going to chill here. All right. So these moves are pretty cute, right? These are some cute moves. Now, like I said, I think writing them out in the sigma notation is compact and very easy to deal with. I feel like everyone gets like anxiety about the sigma notation. Sigma notation is beautiful. It works really nice. It's beautiful. It might hide some things, but it's making life easier. If you're to write all of this out using the other notation where you actually write out summations of terms, you'd have to write out like 6 terms for each of them to kind of see the pattern. And like pattern recognition, if you're good at it, you can do it that way. But this, I like this way. It's nice. But anyway, so we now know that that's equal to 0. It's a power series equal to 0, so that means all the coefficients must be 0. So that tells me, like I said, this first term's off doing its own thing, so it just tells me, well, C2 needs to be 0. Now, since this is equal to 0, I now know that this is true, and so I can solve. And when you're solving for recurrence relations, again, always go for the index, the biggest sub-index you see. So here the biggest one is n plus 2. So we can solve there for the recurrence relation, right, just by adding the c sub n minus 1 and divide out the n plus 2 and the n plus 1. And I want to stress something here, right? This was equal to 0 when n started at 1. This is only good when n is equal to 1 and beyond, right? And we should immediately see that that's true. There's a problematic result here. If you were to try to plug n equals 0 into this, well, then you'd have c sub negative 1, and that does not exist. Okay, so something to keep in mind, especially when there are some spicier examples where you start at 2. You'll see. It'll be fun. Okay, now that we got that, we want to figure out something. Right. This is a second order DE, which means it has two linearly independent solutions, y1 and y2. So how the hell do we get that from their occurrence relation? Okay. So let's do what we did before and crank out some terms and see if we can notice something. Okay. So C0 and C1, well, they're just C0 and C1. We don't have any information about those. Well, we know C2 is 0. The recurrence relation can then tell us how to compute C3, C4, C5, C6, C7, C8, C9, C10, C11, so on and so forth. And if we plug all those in, we'll notice something. C1 shows up. There's C1, C1, C1. C0 shows up. The fact that C2 is 0 makes a bunch of terms 0 out. And so if we look at these, we see that C0 is associated with certain terms. C1 is associated with certain terms. So I have two undetermined coefficients, right? I have two unknown constants. I can use my two unknown constants to make my two-parameter family of solutions. All right, so here we go. I'm now going to produce to you the fundamental set of solutions to the area equation and give you formulas, power series formulas for the so-called area functions. Okay, so the power series, we just noted that the coefficients are either c sub 0 times something or c sub 1 times something. Something that we can do with power series is rearrange them so we get all the c sub 0 terms together and get all the c sub 1 terms together and factor them out. That splitting of terms is allowed for power series, but it is worth noting that there's some real sticky domain stuff that I'm completely and utterly ignoring right now because I don't want to get into it. Because we need to get into the world of uniformly converging series of functions, and I don't want to talk about that. If you're interested, feel free. We'll do a little Zoom. I'll tell you all about it, but we'll leave it at that. But anyway, so here we go, the area functions in all of their glory. If you look at these, you might be able to wait, I think there might be a pattern. There is a pattern, but it's not. It involves. It's a really. There's a way of doing this with factorials, but you gotta be really careful about how you do it. So if you do look at the wiki or like the Wolfram resource page for the area functions, you'll see they use the gamma function for it, which we're going to talk about that soon. But for the time being, don't even know what that is. So the last thing I do want to note, when you do power series solutions like this, and so you isolate all, this is, by the way, always what happens. There will always be two coefficients that are undetermined that you can then basically split into two parts. It takes some work to prove that these would be linearly independent from each other. Hopefully that goes without saying, but they will be. And then the C sub naught is actually y of 0, which we've talked about. C sub 1, also remember, is y prime. So if I actually had initial values here, I can actually tell you what C1 and C0 and C1 needed to be directly. So that's actually kind of nice. So you don't have to take a derivative to solve for anything there. So solving for IVPs for second order ones is actually a little bit easier with this. But well, there we go. That's one way of attacking variable coefficient differential equations. Checking out power series. Note in this case we're kind of good because x is not multiplying a derivative, so there is no sort of like singular point thing that we need to worry about. Like, ooh, what happens when x is 0? At least for the area equation, we're fine. But other ones, it can be a little bad. But anyway. And that's basically it for the world of variable coefficients, or at least for this course. If you're interested in dealing with variable coefficient equations, I recommend that you work your way up to Math 481, numerical differential equations, where you'll get into ways of getting pictures of solutions, not necessarily formulas. Pictures, tell you some information as well. So, but with that is it. We are done with variable coefficients. But we're not quite done with second order differential equations. We got one more thing we got to talk about before we move on to a different topic. So that will be the story for next time. I'll see you then.